The following is a video lab report discussing Newton's second law and the momentum principle in relation to the falling of a ping pong ball from rest. Morgan Jackson, Dr. Greco, Section MO2. Before I begin, I would like to give an outline of what will be discussed in this lab. In this lab report, I will discuss Newton's second law and the momentum principle as it is associated with the falling object and drag, make two computational models and discuss merits of each, and answer questions regarding terminal velocity. If we begin with Newton's second law, we can see a few aspects of this experiment. As the ball falls, velocity is changing. It doesn't equal zero. Therefore, the net force is not equal to zero. We can also see that since F net is not equal to zero, we can also determine a change in momentum according to the momentum principle. To start, we have to look at different aspects that make up F net in this case. These aspects are the weight force and the force of drag. Weight force is simply the mass of the object times the force of gravity, which is negative 9.8 meters per second squared. To account for drag, we have to include A, which is a constant determined from experimental conditions, and the velocity squared, which is determined by the experimental positions and times. This all will make a bit more sense as the lab report progresses. My experimental approach was to drop a ping pong ball from rest. Here is the raw video of that happening. I simply dropped a ping pong ball and filmed it as it hit the floor. Video was analyzed in Tracker and each individual position was noted. You can see in the upper right corner a graph of the position versus time as was determined by the experiment. The first model I constructed was solely based on gravity. Here is my code. Notice that here F net is just the weight force. In actuality, this isn't the case. This model shown is an okay representation of the falling motion of the object, but there are additional forces on the object that this model does not demonstrate. Here is a graph representing the model position versus time for the first model, accounting for solely gravity. This representation almost fits, but toward the middle you can see that it is a bit of an over-representation. Also, at the end of the graph, you can also see that the ball started experiencing drag a little bit by the way the graph flattens out. The need for a better model is necessary. In model number 2, I use the equation AV squared to account for the drag force, where A is a constant that we have to calculate using final position. You can see here where I edited the drag force to be the magnitude of the velocity times the unit vector, where the blue arrow points. The y component in the unit vector is what I concluded to be A. When the model runs, the goal is to get a value that would produce a final position close to the experimental final position. The experimental final position was negative 0.997, so we can see here that this model was fairly accurate by what's circled in red. By running this modified code, this is the model that results. The blue arrow pointing up is the one demonstrating the drag force opposite to the direction of motion. We can already tell that this model better includes the additional components of F net. Here are the comparisons for both models created. The red line shows model number 1 without accounting for drag, and the orange line shows model number 2 accounting for the drag force, and the blue dots are the experimental positions. We see that the model accounting for drag includes the last point of the experiment position. We can also see here that the model position without drag seems to be a little bit more accurate. This is because the ping pong ball that I used was very light and small, and the drag force has a very small effect on the position of the ball as it traveled downward. The first question to address is, do either of these models predict a terminal velocity? By looking at the previous page of position versus time, we can determine velocity by taking the derivative at each point. To look for terminal velocity, we need to see where the velocity, the slope, of the graph is no longer changing. In the model accounting for drag, the orange graph toward the end, we can see that the graph's slope is no longer increasing. The velocity is no longer getting larger. Here in the model for drag, we can see a terminal velocity. Next, what would happen to the terminal velocity if the ball was thrown downward? The terminal velocity in this case would be the same as discussed previously, however, it would take a shorter amount of time to reach that terminal velocity as the ball was falling. Terminal velocity is reached when the velocity is no longer changing, when the acceleration is equal to 0. An initial downward force would cause the ball to reach that terminal velocity quicker. This concludes my video lab report on the motion of a falling object. Thanks for watching.